Okay, in this video, I'm gonna solve the third problem from the first set of lecture notes from David Tong's course. So we have this Lagrangian here, and we make this this transformation. We have this internal symmetry. So I've talked about this. I did an example doing a similar kind of thing before, where our potential is just a function of psi times psi star. So this is just a specific example of that. And we know that if we make this kind of change, this is just the infinitesimal version of this finite transformation, where we multiply psi by just a phase, e to the I alpha. So if alpha is infinitesimal, then I can just Taylor expand this. This will become 1 plus I alpha. And so the change in psi will be this term. And correspondingly, the change in psi star will just be, take the complex conjugate of this. And so it'll be minus I alpha. So, so it's pretty obvious that this Lagrangian is invariant under this transformation because we always have a psi star and a psi. So we'll always have an e to the I alpha. If we plug this in here, we'll always have an e to the I alpha times an e to the minus I alpha, which is 1. So it's completely invariant under this kind of transformation. You could also plug in this infinitesimal version. So plug in this here, and you will get that so you'll have, you have to FOIL something here, and you'll find that the cross terms cancel, and then the last term is quadratic in alpha, which is infinitesimal, so you just throw that away. And yeah, it'll still be invariant under this. So so the first thing it asks us to do is just find the equations of motion, but first I'll find the conserved current. So our formula for the conserved current is this. And so here we have we treat psi and psi star as independent fields. So we have two of these terms, and we get no extra terms in the Lagrangian. So f is 0. So our current will just be will just be this. And so these are easy to calculate. So dl d mu psi. Again, these are independent fields. So if I do d mu psi, I will just get a d upper mu psi star. And then delta psi is, again, we leave off the infinitesimal parameter when we write it in here. So delta psi is just I psi. And then similarly, dl d mu psi star will just be d mu psi. And delta psi star is minus I psi star. So this is our current. And we want to show that it's conserved. So basically that d mu j mu is 0. So if we calculate d mu j mu here, we use the product rule. So we'll have psi d mu psi star plus d mu psi star, and then minus psi star d mu psi. There should just be psi. And the last term is minus d mu psi star d mu psi. So these two terms are the same thing. So even though, we have an upper index here and a lower index here, but if we have two things, so if I have two vectors contracted like this, I can just write this as this but then I can apply, so I've just, you know, n mu nu is times y nu is this will raise this, so it'll become y nu. But instead I could act this on x, so this will become x nu y nu. So it doesn't matter which thing has the upper index, which has the lower index when you're contracting things. So these two terms are equivalent, so they cancel. Go away. And I'm just left with these two terms. So we can't do anything else with this yet. So now we need to, if we calculate the equations of motion, so we will get these two equations. So we already have dl d mu psi and d mu psi star. So the Euler-Lagrange equation, the first term will be d mu of this. So it'll be d mu psi star. And then the derivative of the Lagrangian with respect to psi is just negative m squared psi star minus lambda psi star squared psi. So you'll get this. You should probably work it out if, But yes, we get this, and then we can just take the complex conjugate of this to get our other equation of motion. And so notice, so we have in our current, we have this d mu psi star, and this d mu psi. So we can just solve these two equations and get equations for those two things. And if we just plug those in here, so this thing will become I, so we'll have the psi times this, which will be minus m squared psi star minus lambda psi star squared psi, and then minus psi star times minus m squared psi minus lambda psi squared psi star. And this term, so we'll have minus m squared psi star psi. This term is positive m squared psi star psi. And this term is also minus this term, so everything cancels. And we get 0. So our conserved current is indeed conserved. So yeah, so in general, that's how you have to prove that the conserved current is conserved. First, you calculate what the conserved current is using our formula, and then you'll have some expression that you can simplify using the equations of motion. And once you plug in the equations of motion, you will get that the current is conserved.